What's up, Dr. Zhang? My name's Austin Thibodeau in Engineering 311 Fluid Mechanics. I'm be doing my video project today, proving the flow rate equation. To do that, I've constructed my own bucket using PVC pipe, caulk, and 5-gallon bucket. So the first part of this project was getting the supplies. I had a 5-gallon bucket that I had laying around from Lowe's. I had a coupling right here that I glued and caulked around to make sure there wasn't no leaks. I cut a 1-foot-long, 3/4 inch stick of PVC pipe, and then have a cap here at the end to make sure the water doesn't flow out until I'm ready. So taking the appropriate measurements, the diameter of the 5-gallon bucket is right at 1 foot. The length of the pipe coming out is 1 foot, not counting the cap because the cap won't be on whenever I drain the water. And then the height of the bucket comes out to 14 inches. Okay, so as you can see, the water is leaving the bucket through the tube. There's no leaks with my caulk. I have the timer going also on my phone. When this bucket completely empties, I'm gonna stop the timer. I'm gonna do this 3 times and then average the times out to see what the average time it takes for the water to drain the bucket. First, looking at the free body diagram that I have the pressure points labeled 1 and 2, where these are both gonna be open to atmosphere. I have the gamma of water, viscosity of water. I have the heights labeled all appropriately. I looked up surface roughness of PVC pipes, which comes out to about that number right there on every single website I looked at. Had the Z axis designated. So I took the measurements all from the bucket and the pipe outside. I converted all the inches into feet. That way all the units would be the same. And right here at the bottom, I have this little table of the times that it took for the water to exit the bucket. I took 3 different trials and then I averaged it out to be about 44.71 seconds. But this diagram right here is going to be the basis of what my equation is going to be based off of. The real important parts to notice is where 1 and 2 are, is that they are both open to atmospheric pressure. Okay, so the next step is going to be our equation analysis. I have your classic Bernoulli equation set up right here with the sum of the head losses in here. Because anytime you have a system like this, there's going to be some kind of head loss that you have to interpretate in here. So canceling all the appropriate ones out, cancel P1 out because it's open to atmospheric pressure. You cancel V1 out because the incoming velocity is 0. You cancel P2 out because, again, open to atmospheric pressure, so it's 0. And Z2 on this axis is going to be 0, where Z1 will be at the very top. That corresponds with P1. So solving everything for Z1 gives you this nice little equation right here, with this being the frictional head loss, this one being the entry head loss, and this one being the exit head loss. You're going to take all of this and solve for V2 since velocity is what you're looking for, and you're going to use your KS over D to do that. Now, using the Moody diagram, I guessed 0.020 with a velocity of 3.2 feet per second is where it converged. So there's 2 ways to solve for the flow rate. One way is Q is equal to velocity times area, which is this little nice equation right here. It gives you that value. And the second way is volume over time. So solving for the volume right here, and then solving for Q right here. You can see that the values are not that different. So the experiment was a success, and I hope you like my video project.